Let's talk about the integral test. So in this video, we're going to talk about the statement of the test, and then we'll use it on two examples, which you can see down here. In class, we'll talk about kind of why this test is true, and then some implications of it. Okay, so what you're seeing on the screen right now is kind of my interpretation of this test. So this is different from what you wrote down in your notes. Feel free to pause this video if you'd like to copy it down exactly. Okay. So what I have in the box here is not just the statement of the test, but kind of broken down into pieces. So the first comment here is that the integral test is used to answer the question, does this series converge or diverge? That's the question that we're answering for the next couple of sections. This is just kind of the question, and we're going to need a lot of different tools in our toolbox to cover a lot of bases. So this is one test of many that we'll end up collecting. That are used to try to answer that question. So here's a series, does it converge or diverge? Okay, so I'm going to talk about an f of x, right? So you start with some series where a sub n is like our placeholder for the formula for the terms, but then we use this f of x in the test. So I want to clarify here as like a separate bullet point. F of x is the continuous function version of the formula that you see. And we'll talk about that in the two examples that I have below, kind of what that means. But essentially, you're taking the formula that's here, and you're putting it in here as like a function formula instead of a series formula. So it's the same thing, it just usually literally has an x instead of whatever letter you started with. Okay, so these last two bullet points are the actual statement of the test. Now, there are some conditions that your series, and its f of x that goes with it, has to match. And this is not always met for each series, right? So this is something that's like only in special cases does this happen. So the function that goes with your series has to be positive. So no negative y values for your function, at least for the interval that you're looking at. It has to be continuous. So that means like no asymptotes in the middle of this, no discontinuities, no jumps. Usually that's easy to. It's a low bar to meet, I guess. And then the third thing we need from that function is for it to be decreasing the whole time. So this is going to take out a lot of sine and cosine functions that will wave as you go, anything like that. They have to kind of be going down left to right the whole time. So as long as these three conditions are met, then the test says the following. Your series converges if the improper integral, so this is the integral of f of x, so f is the function version of that formula there. And then it has the same bounds on it as the series. So the series goes, n equals whatever number to infinity. This improper integral will go from that same number to infinity. So you essentially have an improper integral problem. You want to compute that integral, decide whether it converges or diverges. Whatever you get in terms of that answer, that's your answer for your series as well. So if this converges, you say converge. If this diverges, you say diverge. If it converges and you get the exact value, that's actually not helpful in this context because these two things aren't necessarily equal to each other. Like they're probably not equal. It's just they'll both converge or both diverge. Okay, so let's see this thing in action. It's a lot to keep track of, but in practice, it's a little bit more straightforward than it might seem. So the series that I've chosen for this is actually very intentional. So we have the sum from k equals 1 to infinity of 1 over k squared. Okay, so the first thing we want to do is decide what the f of x is here. So f of x is supposed to be like the function version of this formula here. So here I have a k instead of an n, but all the rules should be the same. So instead of 1 over k squared, my f of x will be 1 over x squared. Literally just the exact same formula, but I'm using an x instead of the k or the n that I started with here. And the change that's happening is that we're now thinking about this as like a function, so you can plug in any number at all, right? You can plug in pi and root 2 and stuff, whereas here it's only 1, 2, 3, 4 that go into it. Here it's like a literal continuous function that you can graph. Okay. So we want to decide, does the integral test apply? So we have to meet these three requirements. Is your function positive, continuous, and decreasing, at least on 1 to infinity, right? Anything that happens to the left of 1 we actually don't care about. All right, so is it positive? Yes. right? 1 over x squared is always positive numbers no matter what, so we're good there. Is it continuous? Yes. And that's actually kind of a maybe for a minute there. So 1 over x squared is not always continuous, right? It has a discontinuity at 0, but since 0 isn't from 1 to infinity, right, it's kind of outside of where we care about, then we say, yeah, it's fine, at least where we care about. And then finally, we want to decide, is it decreasing from left to right? And this function definitely is, right? We've seen the graph of this guy a couple of times. It's just going to go down. The bigger the number you plug in, the lower you go here. So this f of x satisfies the requirements of the integral test, so the test applies. So what we want to actually compute is the integral from 1 to infinity of 1 over x squared dx. So this is just a throwback to the improper integral section, and they'll all be what we call type 1 with infinity as that upper bound. Okay, so we're actually going to save ourselves a little bit of work. I picked this example because it's exactly the improper integral example we did in the video of that section. And for you, that was weeks ago, but for me, I made that about an hour ago, so I still have the paper. So what I have here, I'll kind of back up so you can see more of this at once. So what I have here is the paper from the video Improper Integrals Type 1. So we did the integral from 1 to infinity of 1 over x squared dx, right? So you have to put the limit of b going to infinity and put a b there, you do your antiderivative and so on. We'll kind of rip off the work that we've done. We said this is convergent because the limit existed right here. That's actually what we're going to rip off, the fact that this integral is convergent. By now we also know the p-test, so you could also say, oh, you know, p equals 2, I can tell this is convergent. That's just as good. But we'll say, okay, you know, I've pre-done this work, that's convergent. I actually don't care what it equals, even though I know it equals 1. So, okay, this is convergent. So, by the integral test, so is my series. So the series k equals 1 to infinity 1 over k squared is convergent. That's how the integral test works. So when you get something that for some reason you already have done, or like the p-test applies, there's very, very little work kind of in this end here. But if you get something where you can't just look at it and decide, you're actually going to have to do the improper integral stuff, right? So you do the limit, you do the antiderivative, and so on. So there may be some more work built in there, but for the sake of this video, we'll keep it short and just use one that we already have the answer to. Okay, so let's move on to the second example, which is here to provide some contrast. So this series, we have 2 to infinity of 1 over root n. For this series, even though it starts at 2, the p-test will still apply. So we can skip some of the work as well, but it's going to go the other direction. Okay, so if my formula here is 1 over root n, the continuous function version of that is 1 over root x. Again, just the exact same formula, but I put an x in as the letter, and now my eyes are seeing it as a continuous function, which if I graphed it 2 to infinity, it would look pretty much like this. Just a little bit different in the details. Okay, so for all the same reasons as above, this is positive, at least where we care about, it's continuous where we care about, and it is decreasing where we care about. Okay, so that means that the test applies. So now we want to consider, oops, not 1 to infinity, 2 to infinity. I'm using a 2 here because there's a 2 here. 1 over root x dx. So you can see, even though there's a 2 as my bottom bound, I say, oh, you know, this is the p-test, this is 1 over x to the 1/2. The p-test tells me that this is divergent. So I'll skip the work and just say, okay, I know that this is divergent, so that means that this series is also divergent. And that's my final answer. So this series that we started with here is divergent by the integral test. And you can start to see from these two examples that what we have through the integral test is essentially a p-test for series, where all the rules that we knew for this part of the p-test all those rules are also going to apply to series, but we'll talk about that more in class and kind of organize it as its own rule.